So the sixth and final part of our internals discussion is going to describe how a parallel stream is actually constructed and executed. So this is where hopefully all the various pieces we've talked about come together, and you can see how the runtime system of Java streams actually works when you write a stream. So the first thing to remember, and you'll see why this is the case in just a second, is that intermediate operations are lazy. And they don't actually start to run until a terminal operation is reached. So kind of think like the Indy 500, when you put the green flag down, they start to run, right? But until that point, when they're getting themselves in position and lining up at the starting gate and so on, or the pole positions, whatnot, they don't actually run. They're just idling. Okay, so a stream pipeline is constructed at runtime using an internal representation that's based on a linked list. And so what's interesting about this is when your code runs, when you run your program, you remember you've written code and it's turned into bytecode and it's running and so on. As this code runs, it's actually not doing anything when it sees stream or map or filter or sorted. Well, I take it back. It's doing something. It's not doing those operations. Instead, it's building up a linked list of these operations. And so these things are basically being pushed on to the linked list. And each of the aggregate operations you see here, or more specifically the intermediate operations you see here, are being pushed on to this linked list. So we'll end up with a linked list of aggregate operations or intermediate operations, along with the behaviors, which are the lambdas or the method references that are passed to those aggregate operations. Remember, aggregate operations or intermediate operations are higher order functions, so they're basically just lambdas or method references. Okay, so we end up with a linked list of these things, and then you have one for each stage of the stream in the overall pipeline. Any questions about that? So it's actually not doing anything other than building this linked list when it runs. Up until the point it hits the terminal operation, of course, and then that's when it starts to do something. So each stage in the pipeline, right, so the linked list thing that's for the map, for the filter, for the stream sorted or whatever, those are described internally in the internal data structure that Java Streams framework is managing on your behalf. There's a flag that keeps track of, or there's a bitmap of flags that keep track of properties about that stage in the pipeline. And these flags are basically a subset of the flags that can be defined by a split iterator. And of course, split iterators work on the input source. So those also have flags as well. And we'll see how those behave too. They're considered as part of this whole thing too. So here are some of the flags. There's a flag called sized. Do we know how big the stream is at this stage? Yes or no? Is the stream at this particular stage distinct or not? What would be a situation, just off the top of your head, where a stream would start out with distinct values? What would be an example of something like that? What are some data? Yeah, Andrew. Oh, great, range. That's a good one. Range would be one, because obviously, hopefully there's no duplicate values in a range, otherwise there's a bug. What would be another example of a source, an input source that is going to be unique? What's a data structure we've just talked about numerous times? A set, right? So a set will also be unique. In contrast, a list will be non-distinct, right? It won't have the distinct flag set. Another property are the elements of the stream known to be sorted at the point at the stage in this pipeline. So once again, if you had a tree set, that would be sorted. If it was a hash set, we don't know if it's sorted or not, so we wouldn't be sorted. And then the final flag here is ordered, and that just says, does the stream have a meaningful encounter order? Remember how we talked about how a list was ordered, but say a set was not? The encounter order doesn't matter. So those are some of the things that would be set here to make a difference, and we'll talk about those in detail in a second. For example, array list as a source of input is sized and ordered. A hash set is sized and distinct. A tree set is sized, ordered, sorted, and distinct, right? So that's got the full kit and caboodle here. Yeah. If it was an infinite stream, right? So if you had like a generator of some sort, or iterate. If you did iterate or you did stream generate, you wouldn't know how big it was up front. Pretty much anything that comes out of a collection is going to be sized. Each intermediate operation affects the stream flags, right? So this is kind of interesting. So map will clear, sorted, and distinct, but it will keep sized. And that's because map doesn't know what you just did to the input. You could turn them all, to random numbers, right? It'd be a strange implementation of map, but you could take an input stream and make all the numbers random. So you don't know if it's sorted. Also, you don't know if it creates duplicates, so it might not be distinct anymore. Filter keeps sorted and distinct because it doesn't actually change the contents, but it may produce a smaller number, so it's no longer sized, right? Because it may be less, so it isn't the same size, and you don't really know how big it is per se. Sorted keeps sized and distinct and adds sorted. So it doesn't remove any elements or add any elements, hopefully, unless it's buggy. And the elements are distinct. If they came in distinct, they'll remain distinct, but it adds sorted. So as the pipeline is being constructed, the flags at each stage are updated, and they're updated based on the previous stage's flags plus whatever the new stage is doing. So you're basically building up these set of flags. Now, you might ask the question, why the heck are we doing this, right? What is the possible win of building up this intermediate representation and setting all these flags? How is this helping us? Well, it turns out that because streams are evaluated lazily, and because we know the metadata about the various stages, the streams framework can optimize certain properties of the program. If anybody here has ever worked with databases, you've probably heard of a query optimizer, right? So you take a query, especially for complex queries, and you go through and you optimize it to try to make it faster, just like a compiler optimizer optimizes expressions, right? So in this case, we have a streams optimizer that goes through the stream before it starts to run, and it looks for things that can be optimized. So here's a good example. So here we get tree set, and tree set is already sorted, right? So the flag is sorted. Well, we come through here, we didn't call map, we called filter, so we haven't changed the sorted property. And then we get to this place and it says sorted, right? Well, we know that the streams framework says, aha, this source is already sorted, we haven't done anything to unsort it, and now we're calling sorted. Get rid of that operation, right? So it's a way of getting rid of things that are not needed because they are semantically redundant. So this is another benefit of having a lazy evaluation. It gives you one more chance or another phase for optimizations to take place. So you recall I've said throughout the discussion that they try to use sort of non-determinism. This isn't really quite non-determinism. They try to use lazy evaluation in order to optimize things. And so this is a good example of how you optimize through lazy evaluation. So finally, when the terminal operation is seen, then the streams framework will go ahead and pick some execution plan to set all the wheels in motion. And you can read more about that here at this great link by Brian Getz. And not surprisingly, the plan is based on all the properties of the input source plus the properties of the various aggregate operations that are making up the stream. So it kind of looks at the whole plan at that point and says, aha, here's how I want to run this thing most optimally. So what it does is it first takes a look and says, what kinds of intermediate operations are there in this particular stream? And there are two primary categories. One category are so-called stateless intermediate operations. And these include things like filter, map, flat map, which don't require any state because they're simply taking the data that comes in, transforming it, and passing it on. Those are the ones that are often easiest to optimize. In fact, what happens if you have a pipeline with only stateless operations in it, then even if it's a parallel pipeline, in other words, it's running in parallel, you can have a single pass through the pipeline. So you just take the data and you just run it through the pipeline and you're done, right? What you do is the data is actually kind of pulled through the various phases in this linked list, and we apply the transformation to each phase. So that's what you do if you have stateless operations. And you'll also notice that these will typically consider all the elements if they're stateless. There are also stateful operations, and these include things like sorted, limit, distinct. And what does it mean for something to be stateful? What does that imply to you if it's a stateful operation? Right. So a good example is sorted. You're not going to be able to sort the data in a single pass, right? You have to basically collect it all, or collect is the wrong word, get it all together. And once it's all together, then you sort it, and then you pass it on to the next stage in the pipeline. So if you have stateful operations in your pipeline, as we do in this example here, then everything up to that can run in one pass, and then we have to sort of coalesce it all at that phase, and then we have to run it the next pass. So there'll actually be multiple passes, and we'll end up dividing the pipeline into sections, and each of these things gets to run separately. And then we take the results of that, and then we give it to the next phase. So as you can imagine, whenever you start putting these stateful operations in your stream, it's going to make things more complicated. And especially with parallel streams, it often slows things down quite a bit because they have to coordinate stuff. So if at all possible, of course, try to limit your use of stateful operations. Of course, sometimes you can't because they're necessary for your program, but just be aware that they have a cost. Likewise, terminal operations are also divided up into two categories. So we have the so-called non-short-circuiting terminal operations like reduce, collect, for each ordered. And these can be optimized by processing them in bulk using the for each remaining method on a splitterator. And we talked about this earlier, but you may have forgotten. For each remaining just basically says, go through the splitterator and just do all the processing in one bulk operation. And that'll work if it's not short-circuiting because you just keep going till the end, right? If it's short-circuiting, however, you can't do that because you have to check at the end and see whether or not you're done because you may be finished because you may have short-circuited. So some examples of short-circuiting terminal operations would be things like any match, which just finds anything that matches, find first. Those are examples of terminal operations that terminate or can short-circuit. So the second that they run and they get any hit at all, everything's done. So of course you don't want to do for each remaining because you do them all. We only want to do them up to the point where we need to stop. Now it's probably not obvious at this point what a win all this is, but the real win here is if the streams framework is implemented properly, which it is, you can get performance that is comparable to writing loops where you have very fine-grained control over whether the loop keeps running at any given point in time, because you can basically do a break or a return or whatever, or a go to, God forbid. So you can basically go through your loop and break out at any point. Well, with streams, if you didn't have the ability to short-circuit stuff, then you could have this problem where you'd have to do all this processing even if it was just a waste of time. So short-circuit operations allow you to step around that and make it work more efficiently. Okay, so that is basically the overview of how everything works. Hopefully at this point you've got a better understanding of what the parallel streams framework is doing for you. It's very powerful. If you really want to hurt yourself, go and look at the code. It's really painful. Sadly, not very well documented. Very, very interesting looking. So I've gone and looked at it enough to understand. I need to take more time to look at it to really understand it in detail. But there's that article I pointed you to by Brian Getz called something like, Java Streams Under the Hood. And that has a real nice explanation of how this stuff works. In fact, let's see. Let me finish. I'm going to stop the video and then I'll show you something fun on that page.